Hello and welcome to this new discussion where we look at things that have to do with research, recent or not recent, to be honest, in mathematics and physics, and often that are not talked a lot about. So today, what I'm going to talk about has to do with quantum scrambling across an energy barrier. Now, this is an actual commentary about an actual paper that came out slightly earlier. So that's from December 2023. So quite very fresh and kind of recent. Um, Now, what is quantum scrambling? Well, obviously I'm going to submit to put the link to this article. This is free to read this commentary. But essentially, what they mention it's an analogous kind of concept to that of sensitivity to initial conditions that can be found in classical chaos. Now, classical chaos arises from nonlinear interactions in the system. So if the interactions are nonlinear, then you can actually get some kind of intertwined dynamics and basically some kind of very unpredictable effect. And this unpredictability is often quantified by what is called the Lyapunov exponent, which measures the degrees of divergence, of exponential divergence between two neighboring trajectories over time. So that's a classical concept of chaos. Now, the problem with trying to define chaos in the context of quantum mechanics is that basically the equations of quantum mechanics are linear. So what I mean by linear is that they are linear for what is called the wave function or the quantum state. So the H, the Hamiltonian operator that drives the time evolution of the quantum state is by definition a linear operator, and therefore is kind of never going to lead to the kind of sensitivity to initial conditions that people have in mind. However, there are situations where yet quantum systems can be started in some kind of states, and then over time, the way these states are going to evolve is going to look like a mess. And because we can't talk about a kind of sensitivity to initial conditions or chaos in the same way we would talk about it classically, then people have tried to use the term scrambling to characterize this ability for a quantum system to start in some quantum state and have this quantum state kind of being juggled around, let's say, between other quantum states. Now, what is interesting, and in fact, that's in connection with this. I'm just going to skip through one thing: is that the way this is quantified is described actually here. There is this notion of out of time order correlators, okay, and they are represented by these product commutators. So essentially, you take the commutator of x at time 0 and p at time t, and you multiply it with itself, or you take the product, if you will, of this. And this thing is going to essentially be an analogous thing to what you would do when trying to measure the separation or the divergence between two trajectories over time. And there is a corresponding kind of not Lyapunov, but a sort of exponent that goes with it, and that characterizes a sort of sensitivity to initial conditions in the case of quantum mechanics. Okay. Now, what is fascinating, and that's connected to a previous discussion we've had, and maybe some of you have seen, is that actually what they've used as a technique is described here. So to actually get to that technique, and to get the insight about quantum chaos. So again, time-related stuff. They actually used a ring polymer molecular dynamics kind of model, and so that's this isomorphism. So isomorphism basically that iso, this is equivalent, and so morphism transformation. So basically one particular situation transform kind of one to one into a similar, an equivalent one. And so here, that's one that we had discussed before. That's the case of a quantum point particle, for example, or point particle or set of point particle interacting with, let's say, traditional potentials, and this is converted into essentially a classical system of looped kind of polymer with like beads, like so-called kind of bead spring models. And then these are classical, and yet they convey and enable time analysis if we forego interference mechanisms that is basically identical to what quantum mechanics would provide. And so, in this particular context, that's what they used to actually show that these kind of things could actually be observed in as simple a system as basically a double well, so-called double well potential. Now, what is fascinating, and I'm not going to go into that further, I will leave you have a read at the paper, is that they essentially look also at a sort of an upper bound to this scrambling thing, which is related initially to a result that was derived for black holes. And they actually basically look at this result and find very strong similarities for the very simple systems they look at, which is a simple system with like a two well potential. Um, so again, just to tell you that there are plenty of very interesting things that often tend to not be kind of talked about, and here we also kind of leveraged some of the about some fascinating connection between the classical and the quantum. Okay, so on that note, I'll leave you here. If you've got any questions, comments, or anything, please let me know in the comment section. And otherwise, see you in the next video.